In this video, we're going to talk about Leibniz notation. That's a notation for the derivative. So far, we've been using this notation, f prime of x. That's the derivative of f at x. That was due to Lagrange. He's the one who introduced that. But Leibniz had an alternate view, and it's useful to use. So let's take a look. Where does it come from? Well, the derivative of f at x is the average rate of change over some small interval that includes x. Now, average rate of change is the difference in the y values divided by the difference in the x values. So Leibniz used this idea of average rate of change to introduce a notation. He looked at the d's and he called those are the differences, and he looked at the y and x values, and he abbreviated this entire expression, difference in y values divided by difference in x values, and he abbreviated it with just d and then y, d, and then x. So dy dx is the derivative of f. So this is Leibniz's notation. They mean the same thing, but they're just different ways of expressing this idea of derivative. Okay, let's see the Leibniz notation in action. Here's an example of a problem. Use Leibniz notation to express the derivatives of the following functions. So the first function, the number h of tons of hay harvested each fall is a function of the number r of inches of rain that fall in the prior summer. So here the variables, the dependent variables h, that's sort of the y variable, and the independent variables r, that's sort of the x variable. So instead of dy dx, we're going to write dh dr to indicate that h is depending on r. This is the average rate of change in h as r changes, but at the infinitesimal level. Okay, let's look at the second example. The percentage A of carbon dioxide absorbed in the ocean is a function of the temperature, capital T, measured in degrees Celsius. So here, the output variable is A, that's the y variable if you like, and the input variable, T, is the corresponding input variable. So we have, in this case, dA dt. That would be the Leibniz notation for the derivative of this function. The Lagrange notation would be a prime of capital T. That's the Lagrange notation. Here the Lagrange notation would be h prime of r. One advantage of the Leibniz notation is it gives us an idea immediately of how to think of the units of the derivative. So what are the units associated here? Well, it's dh dr, and so it's a ratio of the tons per inch of rain. So tons per inch. Those are going to be the units for the derivative here, because the h has tons, the r, which is the number of inches. So the denominator has inches. So you could also write this as tons per inches. In this example, dA dt, well, A is measured in terms of percentage, so you would write percent, and the temperature is T. So it would be percentage per degrees Celsius. Those would be the units.